All right, so there are two-tier architecture here, two-tier approach, uh, two-level hierarchy is followed in OSPF in order to provide scalability, uh, so that there will be one transit area and all other areas surrounded that will use the transit area to exchange the routes of one area to the other area. The routes of regular areas are only distributed via a transit area. Not possible for a regular area to distribute directly, unlike ISIS. ISIS is totally different in this particular aspect. Now, what I want to show here is there is a need for an area 0 in order to distribute routes from one area to another area. Without area 0, not possible. No areas can share routes. You must have area 0. OSPF is not designed to take the routes of area 1 and give it to area 2. See, even if there is a wire here, as I was telling you, I remember I told you this yesterday, but I'll repeat it today. What is this? My pen is not working. Let's say I have a link here. F and G will not form neighbor in first place. It won't form neighbor. The reason is this port is in area 2. This port is in area 1. When the hello packets are sent, the area ID is compared and neighborship comes. If area ID same. Let us assume this part is also area 1. Let us assume that this is also area 1. This port. Let us assume. Now the routes of area 2 will not be given to area 1. Even though it's the same router which has got the membership with both area 1 and area 2. G router will not take the routes coming from D, give it to F. It won't give. Even though G and F may be a neighbor, you can form neighbor by putting this port in area 1. This port also area 1, that port also area 1. They will form neighbor if the area ID matches on either side of the wire. But because there is no area 0 in this router, routes will not pass. Not possible. So area 0 is mandatory. Cannot avoid. What are the advantages? See, if you don't have area 0, you cannot combine other areas, which means all routers will be in one big cluster, one big group. Where will you summarize? Because you got area, you got a border for each area, and you can summarize the networks of area 1 on this border. Area 1 networks you summarize on router C. Area 2 networks you summarize it on router D. Area 3 networks you summarize on router E. What is summarization? Rounding it to major network. For example, in area 1, 10.1.1.0. Goes like that till let's say 10.1.255.0. Likewise here in area 2, 10.2.1.0. Goes like that 10.2.255.0. Even though all the networks are 10, they are subnetted. This is 10.2.1, this is different network, this is different network. And here, let's say 10.3.1.0/24. 10.3.0.25, 255.0/24. Now, if I don't do summarization, on router B, how many networks you will see? The networks coming from area 1 is 255. Network coming from area 2 is another 255. Network coming from area 3 is another 255. So that will be, let's say around 750. It's 765 actually. Let's round it to 750. 750 routes in the routing table of router B. Not only in router B, on every router in this autonomous system, area 1, area 2, area 3, area 0, on every router there will be at least 750 routes. But when I do summarization, that can be reduced. How? When I do summarization for those networks that are coming from area 1, I do like this. I say 10.1.0.0/16. And here I say 10.2.0.0/16. And here I say 10.3.0.0/16. So now how many networks? Only 3 routes in the routing table. Summarization is very effective. Summarization minimizes the routing table entries. So we got a summarization point. That's why we were able to minimize the routing table entry. We got summarization because we got areas. We got summarization point because we got a border. If no areas, no border, no ABR, then summarization cannot be this neat. So for each area, you got a decent place to do summarization, which minimizes the routing table entries. So on area 1, F router, how many routes you will have? Locally, you got 255 network. Coming from other area, 2 networks, just 2 networks. 255 plus 2, 257. It's the same number of routes that you will also see in area 2 and area 3. In area 0, you will not have these many. Area 0 will have less number of networks. So area 0 is a transit area. If it is having less number of networks, it is good. Area 0 is going to only have summary of the networks coming from every area. The transit area should not be too heavy, it should be light. And it is light. Good. It's good. So areas are good. You can minimize the routing table entry by doing summarization. Secondly, if one of this network goes down, let's say this network goes down, 10.1.3.3.0 is going down. that will be localized. Because that may not be a relevant information to be advertised to other area. The other areas are in other area because they don't talk to these networks often. That's why we have put them in another area. All the frequent talkers will be in one area. Area 2, area 3, they rarely talk to area 1. For area 2 to know 10.1.3.0 is gone down is unnecessary. See, if a train has been cancelled in Uttar Pradesh, who cares? I'm in Bangalore. You are in Sydney. The message someone gives you in the newspaper, train, the 8 o'clock train starting from this station is cancelled. What is the use of that message? For me, it's nothing. But that message is more relevant for local guys in UP. So when a small subnet goes down, if that is informed to every router within an area, it is good and that happens. But because I have summarized, it won't go to other area. That is good also. It is not impacting the whole topology. The impact has been localized within the area. Next. Again, the same thing explained in another word. Because you do summarization, detailed LSA flooding is stopped. Meaning sending detail, this subnet, all those things are stopped in the boundary. Only the summary is flooded, not the detailed. Flooded means what given to others. So for these three good reasons we need this hierarchy network design. Do you have any question on this?
No, sir.
Now this CDE are the boundaries, the area border router, where we do summarization. A and B are called as backbone router. And F, G, H are internal routers. F, G, and H, they are internal to the radius. Even A and B is also an internal to area 0, but they got membership in area 0, so they also have another name, backbone routers. The hello packets are exchanged every 10 seconds after neighborship. And even to discover neighbor, it's the same hello packet that is going to be used. You see, when you meet someone, you started the conversation with hello. And you became a very thick friend, but still you keep calling every now and then and you start your conversation with hello. Only when you don't call for a long time, he may think that we are no more or something like that. So hellos not only discovers neighbor, hellos also maintain neighbor. Keep the neighborship active. So these hellos are sent every 10 seconds. If there is a router which has not discovered earlier, will get discovered now because your hello goes there. From that hello, he is going to understand that you are there. And when he says hello, you are going to understand that there's another new guy there. In this hello packet, there are some informations that are shared. Like we say, hello sir, I am so and so living in this area. Likewise, when a router introduces, it introduces with its name called router ID. Every router has got a router ID. Like we have in this picture A, B, C, D, E. Why should I have A, B, C, D, E? Why not I have A in all router? If I have A in all router, that cannot be an ID. Because I got A, which is different from the character B. Because I got different alphabets, they are unique here. That is A router, that is E router, that is D router. Likewise, OSPF will pick any 32-bit address as a router ID if you don't configure a router ID manually. See, router ID can be configured manually, but when you don't configure it, it will pick from the interface IPs. Loopback interface. If no loopback, then from physical interface. We'll deal with that in some time later. We'll learn those things later. Now, what I'm coming to say is, in a hello package, there are some parameters shared. There are some information shared. In those informations, there are few parameters that must match with the neighbor. Only then neighborship comes up. For example, the area ID must match. When router A send a hello packet with the area ID 0, C, B, D and E, if they are also in area 0, then the area ID matches. So A will be accepted as a neighbor. So not only the hello pack area ID, even the subnet should match. They all should be in same network. Same network, the subnet mask should be of same length. Authentication, if enabled, that also should match. There's a concept called stub in OSPF. In OSPF, there's a concept called stub. That stub type also should match. Stub. The stub type also should match in order to form neighbor. What is stub? This is not the stub like what you see in EIGRP. So there in EIGRP, we saw 5 different types of stub. The purpose of stub there is to say, I'm capable of only this much. You can query only things related to this. But it's not the same idea here in OSPF. It's different. Here it says, I will not accept this. So I'm this type of stub. Say, for example, if I'm totally stub, I will not advertise. I will not receive advertisement coming from other area as well as external. We'll talk about stub also later. It's a big topic. We need to learn different type of LSAs to understand stub. What I'm trying to say is, every router send a hello packet. That hello packet carries some informations like router ID, area ID, subnet, neighbor list, timer. Timer also should match. The hello timer is 10 seconds. Dead time interval is 40 seconds. This also must match with both the neighbor. When they compare the hello packet, they will look for these things to match. Like what? What should match? Area ID should match, and timer should match. The subnet should match. Authentication should match. Subtype should match. When these things matches, they both agree as neighbor. The routers accept themselves as neighbor, their neighbor. And to continue the neighborship, to guarantee that I'm still there, whatever I gave you as an advertisement is still available, I keep sending hello every 10 seconds and you receive it every 10 seconds to maintain the neighborship in your neighbor table. See, forming full adjacency. So in order to form neighbor, hello is enough. In order to form neighbor, just hello is enough. But that is not forming full adjacency. Full adjacency is sharing something. That's what going to form full adjacency, isn't it? In the real world. A thick friend. What is thick friend? Just forming friend, you need to have hello. That's all. You say hello, that's all. That's just a neighborship. But a good friend, oh my blood brother, that's how Africans will say. They're nowhere related through blood, but they will say, oh my blood brother. That's how they will greet. Which means they are thick friends. What does that mean? It means that he has shared Jola fried rice with chicken to him, and he has also shared Jola fried rice with chicken to this guy. That makes them blood brother. Full adjacency. So what I'm trying to say is, to form neighbor, you send a hello. After knowing neighbor, you if you can share everything to him, and if he will share everything to you, and when you both get fully synchronized, that is what called as forming full adjacency. Full adjacency is knowing each other thoroughly, completely. Nothing about him I missed. I know everything about him. Likewise, he says everything I know about you. Nothing I have which I don't know. So that's complete understanding is what adjacency. So it's more than a neighbor. Adjacency is more than neighbor. When we are having point-to-point WAN link, what does that mean? Whenever you got a serial wire, this is how we draw a serial wire, a zigzag line. R1, R2. Whenever we have a serial wire connected between these two routers running OSPF, they will have full adjacency. They got full adjacency. So after saying hello, they discover. After discovering, they also exchange their database. After exchanging the database, if there is any query, they clarify those queries by sending LSR and LSU, links to the request and links to the update. and they get fully synchronized. This we call as full adjacency. That is what that first line says. Both the neighbor become full adjacent, meaning everything that router 2 knows, router 1 also knows, and vice versa. Whereas in LAN links, what is LAN links? When we say LAN link, it means you got a Ethernet wire. This also may look like a point-to-point, but it is not really point-to-point. We should not, according to OSPF, because you got an Ethernet wire, you cannot call it as point-to-point. Ethernet wire. Why? Ethernet links are called as LAN links, meaning you can introduce a switch at any point of time and connect more devices. That is why they are LAN device. LAN links. Ethernet links are LAN links. So whenever you got Ethernet wire running OSPF, there will be a designated router and a backup designated router elected. So we have in this picture 6 routers. If this will be a designated router and if this will be a backup designated router, so designated router and backup designated router, all the rest of the routers, like 4 routers, they are called as designated router others. That's the name given to that, other routers. The other routers are called as DR others. Now all the DR others will have full adjacency with these 2 DRs. With these 2 DRs. I say BDR as DRs. Backup designated router and designated router. Full adjacency. I just told you what is full adjacency. Full adjacency is not just knowing hello, hello. It is also sharing the LSDB. Fully getting synchronized. In short, what I want to say is, when you have a LAN link, the neighbors, they will not have full adjacency with everyone. They will have full adjacency only with DR and BDR. With the other routers, they will just have two-way state. What does a two-way state means? I know you, but I don't know your name. I've seen you. And that guy will also say, yeah, I have also seen you. That's all. Nothing more than that, they know each other. So if I want to know about that guy, I need to go to the person with whom I form full adjacency. See, let's say this is me and this is you. Me and you will not have full adjacency. But you know me and me know you. Because we have seen, just by name we know. Because we both say hello, hello, no? All the routers say hello every 10 seconds. That is how they know. Me know you and you know me. If in case me wants to know about Y, it will be known through whom? Through DR. Because not only me form full adjacency, you also form full adjacency with DR. So DR will advertise about me to you and you to me. It's only through DR. That is why we have the DR. Now, what if we don't have DR? If we don't have DR, duplication. I'll tell about myself to everyone. You learn about me now. And you think that the third guy do not know about me, and you tell him about me, and that becomes a duplication for him. He already know me. But you thought that your neighbor do not know about me, so you advertised about me, which I always already did. So to avoid duplication, if you have a duplicated information, then there will be a loop. To avoid duplication, to avoid loop, we have DR-BDR election. We'll talk about these things in detail later. Here we are just simply understanding the type of neighborship. One is simply neighbor. We call it as two-way relationship. Two-way means, one way means I know you but you don't know me. Then that is one way. If I know you and if you don't know me, then it is one way. Two-way is what? I also know you. You also know me. That is two-way. Two-way relationship. So two-way relationship is what called as neighbors, simply neighbors. Beyond two-way, after two-way, I give everything that I have to you, and you give everything that you have to me. Now we have one common database. That is what full adjacency. Full adjacency is fully synchronized neighbors. Fully synchronized. The database is fully synchronized. That is full adjacency. So in a point-to-point, in a WAN link, both the routers will be fully synchronized. They don't stop in two-way. They don't stop in two-way relationship. They go beyond that. They form full adjacency. Whereas in a LAN link, all the neighbors will not form full adjacency among them. All the neighbors will form neighbor only with the DR, the full adjacency. Only with the DR, they do full adjacency. Alright, so only with the DR they form full adjacency, and they will have only two-way relationship with other routers. Alright. Next is the routing updates and topology informations are passed only between adjacent router. I already told you. Beyond two-way is what? Adjacency. What does that mean? Updates, topology informations. In another word, what I was telling is LSDB is shared. Link state database is shared between the adjacent routers, not simply two-way state routers. Once the adjacency is formed, LSDB gets synchronized by exchanging LSEs. LSEs are flooded reliably throughout the area. So if I have many routers, A gets synchronized with B. B gets synchronized with A. After that, what B will do? It will try to form synchronization with C. C, after getting synchronized with B, C will try to form synchronization with D. This is how throughout the area, the LSEs are flooded and get a synchronized LSDB throughout the area. You remember I was telling in the previous class, within an area, the LSDB will be identical. Now we got the identical LSDB link state database throughout the area. So what happens is the SPF algorithm now runs on the database. For each destination, it will compare the paths and pick the low cost path and put the path into the routing table. All right, that's the job of this Dijkstra's algorithm. It compares all possible paths to the destinations. Where it is found? It is found in LSDB. So Dijkstra's algorithm runs on this database to compare the paths to the destinations. The paths with the low cost path, the low total cost from this router to the destination. The low cost path is picked up from the database and installed into the routing table. This picture shows how a low cost path is identified. It's just for example, they have a picture. Something similar to this is what happens in the real world, the real algorithm. Let us assume that each link cost is 10. Let us assume that each link cost is 10. Now for X to reach G, there are two paths. One path is like this. If each link cost is 10, this is 10 and this is 10, 20 only cost. Instead of coming via D, if you take the other path, which is also another path for G, the cost is too high, you see, 10 plus 10 plus 10, 30. So X to reach G, the best path elected by SPF algorithm, the shortest path of first algorithm is via D. Topology has got all possible paths to reach destinations, but only the low cost path will be picked up and placed into the routing table. Do you have any question on this?
No, sir.
Now this is the last page of today's class. What you see here is how the links to database gets synchronized. Let's say we got a new router, fresh, just configured, and it's in the process of forming adjacency. The two-way state is over. This guy here formed a neighbor only now. He has just formed neighbor. Hello, hello. They accepted as neighbor. Now this guy is sending whatever he has got so that full adjacency can be established. Now this R new receives the packet. This is the packet. When the packet comes, the advertisements, the link state advertisements or the link state updates, they come with a sequence number. There will be a number. Okay, so when a packet arrives, when the update arrives, first thing is, do I have anything in my database? Is this the first packet I'm receiving, or do I have anything? Because I said, it's a fresh first time it receives the update. There's nothing in my database. It's new, totally blank database. So whatever that was coming inside is just added to the database. It is added. After adding, this RN sends an acknowledgement. saying I received your LSU. Thank you. After that, the RN floods to the downstream. It floods the update to the downstream routers. After flooding, based on what it has received, it recalculates, it runs the SPF algorithm to find the path for destinations. Now, is there any question on this part which I just explained?
No, sir.
Now let us say when we receive the packet, we already got some update inside our database. Our LSDB has got some information already. In that case, I'll see whether the sequence number that I have in my database and the sequence number that is coming in the update packet is same. Is it same? If the sequence number is same, then I already got the update. I no need to receive it again. I have to ignore it. In case if sequence number is not same, is it higher? If the incoming is higher, which means I have outdated one. Mine is old one. So what I need to do, I need to just add the new infos with a higher sequence number to my database and repeat the process of sending acknowledgement, flood it to the downstream neighbors and run the SPF algorithm. In case if my sequence number is higher, what does it mean? The incoming is not higher. The sequence number on the packet is not higher, which means mine is higher. So what I should do, I should inform the sender, means I need to go back to this guy and say, hey, you got the outdated one, I got the better one, take this. So RN will send, if RN sequence number is higher, let's say 101, the incoming was 100, then RN will go back and tell to the sender who sent the 100 that you are having outdated one, take my 101. And then the process ends. Any question on this?
No, sir.
All right. So this explains how the LSDB gets updated. Yeah. Links to database gets updated. With this, we stop here. We'll continue OSPF in our next class.